in the history of approximations to pi, so far we've seen that Archimedes proved that pi is between 3 and 1/7 and 3 and 10/71. Now, for close to 2,000 years, the only real method mathematicians had for approximating pi was with polygons. So this was improved substantially by Zhu Chongzi around the 400s AD. He found that pi is roughly 3.1415926. He actually showed that this digit is a 6 and not a 7. So he was correct to 7 decimal places. And this was actually the best approximation anyone had for close to 1,000 years. This wasn't improved until an Indian mathematician, Madhava, in the 1300s. Madhava was able to get 11 decimal places. And even more interestingly, this was the first time when a mathematician approximated pi without using regular polygons. So here's what he did. So Madhava found 3 important Taylor series. Now, of course, they weren't called Taylor series, and it was written in a very different form, but he found the Taylor series for sine x, cosine x, and the inverse tangent. So sine x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and so on. Cosine x is alternating signs again, but now with even powers. And inverse tangent is x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7, and so on. Okay, so Madhava found these identities. I don't think anyone knows exactly how, but nonetheless, he was able to use, in particular, the arctangent one to approximate pi. So, as you may already know, if you let x equal 1 in here, arctan 1 is pi over 4, and so you get pi over 4 equals 1 minus a third plus a 5th minus a 7th, and that's often attributed to Gregory, who was a European mathematician in the 1600s. But as is the case with many mathematical discoveries, it's not really named after the first person to discover it. Now, one very unfortunate thing about this series is that the convergence is very slow. So the error after n terms is roughly 1 over n. And that's very bad, because if you want even 3 decimal places, for example, you would need about 1,000 terms. So this is clearly not an efficient way to do it. But Madhava realized that if you pick a smaller value of x than 1, you'll get exponential decay, so you'll get a much better estimate. So for example, if you pick x equals root 3 over 3, which is what Madhava did, that's pi over 6, and now you get root 3 over 3 minus 1/3 root 3 over 3 cubed plus 1/5 of root 3 over 3 to the 5th, and so on. The trade-off here is that you get some annoying square roots, but it's not so bad. And if you want pi and not pi over 6, you just multiply through by 6. So you can write it in this form as 2 root 3 times 1 minus a third times root 3 over 3 squared, which is a third, plus 1/5 times a third squared, minus 1/7 times a third cubed, and so on. Well, now the error is going to be more like 1 over 3 to the n after n terms. So that's much, much better. And this is the formula that Madhava used to get 11 decimal places. Although there is some evidence that he might have done even better, because there are records of 17 decimal places later among Indian mathematicians. Now, returning to the original bad series, 1 minus a third plus a fifth, and so on, there's a way of repairing this really bad convergence. So the error, like we said, is roughly 1 over n. So if you stop at, say, 1 over 2n minus 1, then you'll get an error of roughly 1 over 2n. But these terms are decreasing very slowly. So you get something that looks kind of like this. Okay, so if you stop at the nth term, you might get this sum here. And if you stop at the term after that, you might get this sum here. Now, since the terms are decreasing very slowly, those numbers are almost exactly halfway above and below the limiting value of pi over 4. So, rather than just cutting off the series there, if we adjust it by half the next term, roughly, we'll get a much, much better approximation. And this saves a lot of computation. It gives much better convergence. But Madhava didn't stop there. He realized that you don't need to stop with 1 over 4n. You could just get an even better correction term. So actually what he found is that a better error is 1 over 4n plus 1 over n. Now, nobody is exactly sure how he arrived at this, but one hypothesis is that he took the errors and took their reciprocals. So 1 over the error should be roughly 4n. And then if you think that there's going to be some even better estimate, then if you subtract off the 4n, you're left with the reciprocal of the thing you really want. And Madhava found that these reciprocals were roughly 1 over n. Okay, so you can get an even better estimate. And we could go one step further. Now if we do this one more time, we'll get an even better error. And the third term ends up being another 1 over n. And if you keep going, you'll get better and better errors, and you'll get a nice continued fraction with very interesting terms. It turns out that the exact formula is 1 over 4n plus 4 over 4n plus 16 over 4n, and so on. So the numerators are 2 squared, 4 squared, 6 squared, and so on. And then these are all 4n. So if we cut it off here to get the first 3 terms, well, the 16 over 4n turns into a 4 over n, and then you can cancel that with the 4's here. So sure enough, we get Madhava's fraction.